Okay, the next is general design consideration for heat exchanger. What are the factors that you should consider when we proceed to design the heat exchanger? Okay, the first is the fluid allocation, whether we should allocate the example in the shell and tube. We have the fluid insert into the example, a main fluid effluent from the process, and we have the another fluid from the utilities. It depends application at the as cooling or whether to heat up the process effluent, a fluid, or to reduce the or cooling the process effluent. Example, if we have the maybe acidic, and also we have the cooling medium, cooling water. So example, how can you decide whether cooling water or acidic to be insert in the shell or tube? So basically, we're gonna refer to this fluid allocation guideline to decide or to define the allocation of the fluid. Okay, first based on the corrosion. Okay, for the more corrosive fluid should be allocated to the tube side. Okay, this is to reduce the cost of the expensive alloy or clad component, because usually tube can be designed or can be fabricated using alloy material. Okay, falling. The fluid that has the greatest tendency to fall, the heat transfer surface should be placed inside the tube. Okay, example, more the acidic, so it has the tendency to fall. So basically, we may place it in the tube part. Okay, it is for better control over the design fluid velocity, and the higher allowable velocity in the tube will reduce falling. That also the tube will be easier to clean when we talk about the maintenance, troubleshooting and maintenance. So on the tube side, it's easier to be cleaned. Okay, next factor is the fluid temperature. If the temperatures are high enough to require the use of special alloys, spacing in the higher fluid in the tube will be reduced the overall cost. Okay, at moderate temperatures, placing the hotter fluid in the tubes will reduce the shell surface temperatures. Hence, the need of lagging to reduce heat loss for safety reason. So this is based on the fluid temperature that we can decide to place in the fluid or allocate the fluid, whether in shell or tube. And the next, the operating pressure. The higher pressure stream should be allocated to the tube side, which higher pressure tube will be cheaper than higher pressure shell. Okay, the pressure drop also affect in the allocated fluid. Okay, for the same pressure drop, higher heat transfer coefficient will be obtained on the tube side than the shell side. And the fluid with the lowest allowable pressure drop should be allocated to the tube side. Okay, related to the viscosity, okay, a higher transfer rate coefficient will be obtained by allocating the more viscous material to the shell side, provided the flow is turbulent. Okay, the critical Reynolds number, okay, back to we had the range of the Reynolds number with the turbulent, laminar flow or transition, you may refer to that. Okay, for the turbulent flow in the shell is a region 200. If turbulent flow cannot be achieved in the shell, so it's better to place the fluid in the tube, as the tube inside heat transfer coefficient can be predicted with more certainty. Okay, for the stream flow rate, allocating the fluid with the lowest flow rate to the shell will normally give the most economic design. So you may compare the flow rate between the example cooling and acidic or the process effluent stream. So which is the lowest flow rate? You may look at the other shell side. Okay, the higher velocity will give a high heat transfer coefficient, but also higher pressure drop. Those high enough to prevent any suspended solid setting should be obtained for the velocity. But if too high, it may lead to the corrosion or erosion. Okay, for the liquid, okay, the tube side, the process fluid should have the velocity 1 to 2 meter per second, but the maximum flow can be used or if required to reduce the falling. Okay, the typical range of the velocity for water is from 1.5 to 2.5 meter per second, and for the shell side is 0.3 to 1 meter per second. Okay, for the vapor, if we handle the vapor fluid, okay, for the vapor, the velocity used will be dependent on the operating pressure and also the fluid density. The lower values is in the following range will be applied to high molecular weight material. Example, if the condition in the vacuum, so the velocity should be within the range of 50 to 70. For the atmospheric pressure, we can have the velocity from 10 to 30. And for the high pressure, velocity should be within the range of 5 to 10 meter per second. Okay, for the stream temperature, okay, the closer temperature approach used, which is related to the different temperature outlet and the for the one stream and inlet to another stream. Okay, the larger will be heat transfer required for the duty. However, related to the greater, if we have the greater temperature different, should be the least should be 20 degrees Celsius. Okay, example, if we have the cooling water as the cooling medium, the difference should be 5 to 7 degrees. Okay, example, refer to the previous example. If we have the acidic, maybe we consider acidic on the tube. Okay, this is acidic. And then we have a cooling water inlet and cooling water outlet. So the difference of the cooling water should be within 5 to 7 degrees Celsius. And if we use refrigerant brine, so we can consider the different delta T should be 3 to 5 degrees Celsius. Okay, the maximum temperature rise in this recirculated cooling water is limited to around 30 degrees Celsius. Okay, care should be taken to ensure that cooling medium temperature are kept well above the freezing point of the processed material. Okay, when the heat exchange is between processed fluid or for heat recovery, the optimum approach temperature will normally not be lower than 20 degrees Celsius. Okay, this is related to the processed material. Okay, related to the pressure drop, if we have the liquid as the process fluid in the system, so the viscosity if less than 1 Newton second per m square, the pressure drop should be 35. The value should be 35. And if the viscosity from the range 1 to 10, and the pressure drop should be within the range of 50 to 70 kilonewton per m square. How about for the gas vapor? If we have high, medium, these are the range for the pressure drop. For the medium vacuum, you can multiply or times with 0.1 times the absolute pressure. For the pressure from the range 1 to 2 bar, you can use this or 0.5 times the gauge pressure. And if the above than 10 bar, you may multiply the system gauge pressure to 0.1. Okay, for the fluid physical properties, okay, this is required for heat exchanger design, such as density, viscosity, thermal conductivity, and also temperature enthalpy correlates that you may refer to the reference table that give you the specific and latent heat or delta H LV example. Okay, the table shows the conductivity material example if we use aluminium and the conductivity material is 202. This is basically is for the tube side conductivity. Okay, and the last factor that we should consider is the falling factor, or we call as dirt factor, because we know that after a certain period, we can start to have the dirt or the corrosiveness of the dirt or the falling on the fabricated heat exchanger. So that's why we should consider heat transfer resistance. In calculating the overall heat transfer coefficient, the heat transfer, or we call as the factor resistance or dirt factor, should be considered to determine the overall heat transfer coefficient. Okay, the selection of the design falling coefficient, this is due to the economic decision after we consider the allowance, especially to decide the thickness of the tube and the shell, and also the shell bundle clearance. So basically, we may consider the allowance or based on the dirt factor as well. Okay, the falling of exchanger will increase the cost in terms of the construction due to oversizing or additional energy due to the poor exchanger performance, and also to cleaning or to perform the cleaning in removing the deposit material. These are the typical value of the factor resistance based on the coefficient. Example, if the fluid is based on the river water, so you may have the range of the, or estimate of the range of the heat transfer coefficient, that you may also consider the resistance or the factor resistance in your calculation.